This video is going to be on the nomenclature and isomerism, in particular the optical isomerism, and this is part of your Unit 4 specification. So optical isomers are a type of stereoisomerism, and these are isomers which have the same molecular and structural formula but different spatial arrangements. The key feature of an optical isomer is its central chiral carbon. This is an asymmetrical carbon atom which is surrounded by 4 different functional groups. So as you can see from the diagram I've drawn below, in the middle there's a central chiral asymmetrical carbon atom, and it's surrounded by 4 different functional groups. The reason I've drawn 2 is because 2 optical isomers are mirror images of one another. And if you look at your hands now and put them on top of each other, you'll notice that they don't fit nicely, and this is because they're non-superimposable. This is the same principle for optical isomers. So the 2 optical isomers, which are mirror images of one another, are known as enantiomers. A solution which contains equal proportions of both enantiomers is a racemic mixture. So, enantiomers each have the same chemical properties when alone in solution. To distinguish them between the two, we shine plain polarized light through the solution, and the 2 enantiomers, sorry I'm struggling to pronounce this word, will rotate this light equally but in opposite directions. This characteristic makes enantiomers optically active. However, this characteristic also makes racemic mixtures optically inactive, and the reason for this is they do not rotate plane polarized light because their rotational effects of the 2 enantiomers cancel one another out, because like I said earlier, the 2 enantiomers rotate plane polarized light equally but in opposite directions. So if you've got equal proportions of the 2, they're going to cancel. So there's 2 ways then of forming racemic mixtures, and these are nucleophilic addition for planar molecules and electrophilic addition for asymmetrical alkenes. In the spec it only actually includes the nucleophilic addition route, but as a stretch and challenge I've seen a few times they've asked for electrophilic addition, so you're kind of getting a head start here. So to the left I've drawn a diagram of the standard nucleophilic addition. This is almost always with hydrogen cyanide, and it's almost always with the carbonyl group, and as you can see I've only done the cyanide nucleophile here. It can attack from either sides, or what you'll say is it can attack the plane from either above or below, and this can form the 2 optical isomers depending on where it attacks. The other route is electrophilic addition, and this is where we have our asymmetrical alkene, and this attacks a HBr, but it could easily be HCl, HI, HF, so don't get too comfortable with HBr. This forms 2 possible things. It can either form the optical isomers, which are here, or it can form a byproduct, which is this. The way you know that you've got your byproduct is because the halogen will be in a very unstable position. Here the halogen is secondary, and here, whereas here it is primary, and we should know that secondary halogens are a lot more stable than primary. Okay, but in terms of our main product, there's also 2 options. The bromide can either attack above and be here, or it can be below. And if we draw this out like an optical isomer, like we have up here, then you'd see that they would be mirror images of one another. Okay, so finally then we need to know about the usage of optical isomers in drugs, and many drugs are optical isomers, or at least have one enantiomer. But whereas one can be perfectly fine for that drug, the other may react in a completely different way in the body, and this is dangerous. And for example, you need to know the example of thalidomide, and this is a drug that was used for morning sickness. However, the other enantiomer caused birth defects. So that's just an example of where one enantiomer can be fine, but another can react in the body to cause harm. So that's all you really need to know for optical isomerism. Sorry about my pronunciation of enantiomers. I don't know why I kept getting confused, but whatever.